So thank you for coming out so early for Fernando Becerra's public talk as part of his thesis defense. Just like to say a few words about Fernando before we start. So before joining us, he was an undergraduate in Chile at the University of Chile in Santiago. And he had a very impressive academic record there. Also found time to write 3 journal papers on a variety of different topics, covering things like star formation in galaxies, ordinary galaxies, and starburst galaxies, and also gravitational stability of streams of gas during galaxy mergers. So all these were done using computer simulations and computer modeling. So not surprisingly, when he came here, he decided he wanted to continue with that. But he also decided he was bored with the local universe. So he decided to look at more exotic phenomena happening at very early times, very far away. And so he started, his first project was on formation of the first stars in the universe, which I thought were believed to be quite different from the stars that we see around us today. We think that they were much more massive. And so he used computer simulations at unprecedented resolution to study the formation of these stars. And they're very important because the chemical enrichment produced by them, we think, allowed stars like our sun to form later in the history of the universe. But after a time, Fernando again got bored. He thought stars were not exciting enough, even bizarre ones. So he decided to switch over and start looking at supermassive, what we think became supermassive black holes eventually. So the first black holes in the universe. So these are very important because they evolved, we think, into the supermassive black holes that power distant quasars, as well as providing AGN feedback to structure ordinary galaxies, like the large elliptical galaxies we see around us today. So the origin of these objects is very uncertain, and the particular scenario that Fernando's been looking at is the possibility that they formed through the direct collapse of gas in small halos at very early times in the history of the universe. And his simulations that he'll tell us about today look quite promising in explaining this direction for the black holes to form. So aside from his research, he has a very broad range of interests. He's been involved in online education, code development, and optimization. He's also very interested in online teaching. And besides all of these interests in computer type work, he's also a superb photographer. So if any of you look at his website, you'll see examples of what I mean. And so I'm pretty confident that if he ever gets bored with computers and science in general, that he might have a profession as a professional photographer. And perhaps if we're lucky, he'll show some examples of some of his work today, not just in science, but in photography as well. So Fernando.
Thank you very much for the nice. Thank you very much for the kind introduction. Just one note, I don't get bored. I just like to explore a diversity of topics. And thank you for the nice summary of my talk too. I might not be able to give the talk now since you already said everything. Well, today I will be presenting the work that I've done in the formation of supermassive black hole seas in the first galaxies. But before going into science, I'm just going to mention all the people who have been involved in this work and who have been with me in this journey. So I'm going to start by thanking Lars, of course, my advisor, who's always been there to support me, encouraging me to go to conferences, to share my work, to collaborate with people, etc. Also, wine and cheese. We have to mention that. I would also like to thank my co-advisor, Volker Brom, who has been my co-advisor for the last 3 years, and we've been collaborating. He has hosted me many times when I visited Austin. And also the thesis committee, Ido, Abby, Daniel, and Anna, that agreed to be my external reader, for insightful comments about my research during the last years. And I have to thank all the CFA community and the astronomy department community too, faculties, students, because all of these people make this a really nice place. Also, we've been doing a lot of stuff with grad students, hiking trips, biking trips. This is the midnight bike ride the day before the Boston Marathon, which is really nice. So if you haven't done it, I highly recommend that. Also, the Hernquist group. Besides group meetings and wine and cheese, we also organize trips, like ski trips or trips to the Arboretum. I don't know if you remember that, Lars, but I'm pretty sure you didn't realize I was taking this picture. Also the administrative staff, Rob, Nina, Lisa, they are really, really helpful, and they are really, really wonderful people. And there's a space there for Peg, because I asked her to send me a picture, and she didn't like being acknowledged. So she actually sent me a picture of a Peg. But Peg is upstairs. So if you turn around, you're going to see her. She's really important in this department. I would like to thank my office mates. We share offices with these guys for 4 years, and we didn't get tired of each other. That's a huge achievement. Even on those times when we were not actually working, people get tired of working on problems, etc. So sometimes we have to take some breaks. By the way, this guy is defending tomorrow, so you can use this against him. Okay, but we also had great time having dinners, trips, movies. This girl is, by the way, it's her birthday today, so happy birthday. Also, we conquered summits, the Mount Washington Summit, Katahdin with the hiking group. I really like hiking, so that's another thing that I could do in the future, being a Sherpa. That's another thing that I can do. All the people that I play soccer with, I don't know if you know, but I really like soccer. And in this case, I really want to thank all the people here, part of that glorious team that won the ITC Soccer Cup in 2016. Woo! Yes. Sorry, Abby, for saying this. But I have to keep showing pictures. I've spent here 6 years, and we've won it just once during these 5 years that I played. So I have to keep showing pictures. Also, Abby might get a bit annoying. Okay, the last one. The last one. I promise this is the last one. Also to people around the globe. So usually I run into friends when I was traveling to conferences, and that's really nice to have a network of friends that probably are watching the live stream now. I hope so. Also, friends from high school, that they are always there for me when I go and visit Chile. We always get together, have fun, and actually there's one of them who came all the way from Chile today. The most expensive defense in history. And my second family here, Chileans mostly, plus partners, and maybe some Argentinian people too. We're fine with those people too. I really, really want to thank them. My family, who came all the way from Chile, muchas gracias por apoyarme en todo desde cuando era pequeño. Gracias, gracias, gracias por venir. Ustedes saben que lo llevo aquí. And Katie, for being such a huge support in these months, for being with me, for being a really, really, really nice person. Thank you. A black slide also for the bad moments during grad school, because not everything is good moments, and sometimes we need that strength to keep going. Okay, enough acknowledgements. Now back to science. So we're going to start this picture with a brief history of the universe. So what we understand of the history of the universe is that it starts with the Big Bang. Right after the Big Bang, the material is ionized, which means that it's mostly protons and electrons just moving around. At that point, light can travel in between these protons and electrons. But at some point, during 300 or 400,000 years after the Big Bang, the temperature decreases, and these protons and electrons start attracting each other and forming neutralized material again. In that case, light cannot travel through this neutralized material. So basically, light doesn't travel in this stage, which means that we are not able to see these edges. That's why they are called the dark age, because they are basically dark to us. But at some point during the dark ages, the first luminous objects start to form. First galaxies, first stars. And these galaxies and stars start emitting radiation, and they start ionizing the universe again in a process that we call reionization. After that, structure keeps forming, smaller objects form bigger objects until we reach the point of the present day here. And what we are interested in are the first supermassive black holes. So from observations, we know that supermassive black holes form at some point before the universe was 1 billion years old. So redshift higher than 6 or 7. The problem with that is that we don't really know how these massive black holes form. And actually, we don't know too much about black holes at all. So this is just an artist's impression of what a black hole might look like. So black hole is this point with huge densities that attract everything, including light. And we don't observe anything inside the black hole. But we do observe the material around the black hole. So in this case, it might form some sort of disk, or material can get ejected, and this is how we observe the black hole. So we know that black holes exist early in the universe because of these kind of observations. So one theory says that these supermassive black holes form from previous supermassive black hole seeds, which are smaller in mass, but eventually grew all the way until they become supermassive black holes. But again, the problem is that we don't know how these seeds form. And this is going to be the main topic of this dissertation. So we start with this picture of what we think the universe looks at large scales. We have what we call the cosmic web, filaments. At the intersection of filaments, we see huge accumulation of matter. That's what we call halo. And as Lars said before, we're going to study one particular scenario of formation of black hole seeds called the direct collapse scenario. So for that, we're just going to take one of those massive halos, and we're going to see what happens to gas. So gas inside the halo falls towards the center, meaning that gas is collapsing to the center. And since all of this gas is falling to the center, eventually it's going to form a protostar, a massive protostar at the center. This protostar then can keep growing in mass, gaining more and more material, and it's going to become eventually a supermassive black hole seed of 100,000 times the mass of the sun or so. And the time it takes to get to this point is roughly 100,000 years. So basically, we can say that this protostar is growing at an accretion rate of 1 solar mass per year, meaning that it's gaining a mass equivalent to that of the sun each year. So one point that is important in the direct collapse scenario is that this protostar needs a high accretion rate, needs to gain mass at a rate of roughly 1 solar mass per year. So this is one important point in this scenario. A second important point is fragmentation. So ideally, we will prefer to have just one protostar form at the very center of the halo instead of having multiple protostars. Why? Because if we have one, it's going to be more massive, which is going to help to become a supermassive black hole seed. If we have many, they might be less massive and eventually have less accretion rates, smaller accretion rates. So how do we solve these problems of having high accretion rates and trying to avoid fragmentation? With high temperatures. So an estimation of the accretion rate of these objects can be done, and we get a relation of this kind. So the higher the temperature, the higher the accretion rate. And also we can estimate the mass of the fragments, the mass of the protostar, as a function of temperature. And we also get that the higher the temperature, the more massive the protostars are going to be. So if we want to avoid fragmentation and if we want to have massive protostar, we just need a high temperature environment. But let's see what happens in the halo. Remember that in this scenario, all the gas is collapsing into the center. So as the gas falls into the center, what we're going to plot here is temperature of the gas, and this is density. As the gas falls towards the center is going to increase in density, okay? But as the gas falls, it starts to heat up, okay? So gains temperature, the temperature increases. Then, when it reaches around 10,000 Kelvin, what happens is that all of that energy that is in the gas starts being emitted. So the gas is basically getting rid of that emission through a process that we call molecular hydrogen cooling. So the gas is getting rid of that energy, which means that the temperature decreases. And this is due to molecular hydrogen cooling. But remember what I told you about temperature and fragmentation and the mass of the protostars? We need high temperatures. So this is not ideal. We need something better than this. So somehow we need to get rid of molecular hydrogen. And there is one process called Salomon process that basically is telling you that if you inject energy into molecular hydrogen, you're going to dissociate that and we're going to get atomic hydrogen instead. So if you want to get rid of molecular hydrogen, we just need a background radiation that photodissociates a molecular hydrogen. Okay, so let's try this theory now. We have the same halo as before, but now we have a background radiation called Lyman-Werner because of the range of energies that the photon have. So now the gas again is collapsing to the center. It's heating up, it's gaining temperature. But now there's no molecular hydrogen because it's being destroyed by this background. So what we have is that radiation still escapes from the halo, but in the form of atomic hydrogen cooling, not molecular. And in this case, the cooling is not as strong as it was before. So remember, the molecular hydrogen cooling drops the temperature to these values, while the atomic hydrogen cooling remains the temperature roughly at the same. This is a stage that we call of isothermal collapse because it's roughly the same temperature. So now we can have the formation of protostars in a high temperature environment, which is what we wanted. High temperatures, more accretion rate, more massive protostars. And since these halos are dominated by atomic cooling, these are called atomic cooling halos. So this is exactly what we are going to explore, and these are ideal places for high accretion rates and to avoid fragmentation. So this thesis, when I talk about formation of supermassive black holes in the first galaxies, is basically the formation of these massive protostars at the centers of the atomic cooling halos. But something that I haven't told you before is that the scenario is not as easy as it sounds. So what happens is that the gas collapses to the center of the halo, the protostar forms, but the protostar is also emitting radiation. That radiation escapes, but at some point we say that the gas becomes optically thick. That means that radiation doesn't escape from the halo. After that, the gas that in principle can form a disk around the protostar tends to form a spherical object, and then this spherical object keeps gaining more mass until it becomes a supermassive star, and eventually this is going to collapse and form a black hole seed. So this whole process of forming a black hole seed has many stages during this process. And in this dissertation, we're going to explore each one of these stages in different papers. So the first paper that we wrote was about the formation of massive protostars at the center of atomic cooling halos. Then the second paper was more about how this protostar evolves after it has turned toward a spherical object. The third paper accounts for the long-term evolution of this object until it forms a supermassive star of 100,000 solar masses or so. And finally, the fourth paper that we're working on, it's trying to implement radiation, which means how this energy coming from the protostar is going to affect this whole picture. So for that, as Lars already told you, we use numerical simulations. So what does this mean? Is that we roughly know how all of these components work in the universe. So we have dark matter that is mostly gravity. Gas, we know the equations to explore how gas evolves. And something important in our simulations is the chemistry. Remember that these halos are dominated by atomic cooling hydrogen and also by molecular hydrogen. So we need to explore how these cooling processes and how this reaction can affect the evolution of these objects. But now we have all these equations, and what we do with all these sorts of equations, instead of trying to solve them in our minds, we just use supercomputers. So this is like many, many laptops that we use, stick together, and they all communicate between them. So we set the initial conditions. We know the equations to describe the evolution, and we just throw all of that into this computer, and this computer gives us a model of how things evolve with time. In particular, I use a code called a repo, which is a moving mesh. I'm going to explain that later. So what this code does is that it divides the space into grids, and these grids move with particles of gas. So this is a gas disk with higher densities at the center. And as we see, as the disk rotates, this grid is moving with the gas. That's why it's called a moving mesh. And we solved all of that set of equations in each grid. So each grid has a value for any property that we want, like density, temperature, mass, etc. And the higher the density, the smaller the grid. That means that it's going to be more expensive to solve the evolution of these cells. The smaller the cell, the more expensive. And this is going to be an important limitation in our work, as I'm going to tell you later. Okay, so now that we know how to evolve this problem, I'm going to tell you about the early stages, how a massive protostar forms at the center of an atomic cooling halo. For that, I'm going to start by showing you a movie. Since we have all the information about the gas at every single point in space, we can just make some images like this one. So this one is showing density, which is basically the amount of particles. This is the scale of this box. Parsec is a unit of measure that we astronomers use. It's just huge. But remember this number. Remember this number, 5,000, because we're going to go well inside the halo, and we're going to reach scales of less than a parsec. And at the center is going to be our halo. At this point, it hasn't formed yet. So we're going to see how the halo forms first, and then how all the gas collapses to the center. So we start to see the formation of the halo at the center. There are smaller halos that collapse to form bigger halos. Eventually, it becomes a massive halo, and the gas keeps falling towards the center. See the density here, it's increasing. We are zooming in to see how this gas evolves in the smaller regions, the regions near the center. And as we continue zooming in, we keep observing the same kind of collapse, gas falling towards the center. Again, zooming in, densities are now 10 to the 8, 10 to the 10, etc. Here, the scale, we started at 5,000. Now we are 0.01 parsec. And the gas keeps collapsing, until at the very end of the simulation, we have a protostar there. So this is exactly what we were modeling. The collapse of gas in atomic cooling halos all the way to the very center to observe the formation of this protostar. Densities now are 10 to the 18. The scale is 0.0001. Remember, we started at 5,000 parsecs. And now it's like, this is tiny compared to the huge halo. I told you that we have basically all the information for the gas, so we can plot besides density, temperature, and molecular hydrogen. Do you remember why temperature is important? Because we need high temperatures to have high accretion rates. Why molecular hydrogen is important? Because we don't need it, okay? We want to avoid too much hydrogen. So here, the values for the temperature start at 10 to the 3 or so. Remember that the gas is going to heat up at the center of the halo. And the fraction of molecular hydrogen is roughly 10 to the minus 12, which is really, really small. So as the halo starts forming, we see the collapse of gas. The gas starts to heat up. It reaches values of 10 to the 4. Molecular hydrogen fraction increases to values of 10 to the minus 10, 10 to the minus 9. This is still quite small because we added this background radiation that destroys molecular hydrogen. If we keep zooming in, the temperature starts decreasing a bit. This is because of atomic hydrogen cooling. And the H2 fraction remains very, very, very small, which is what we expected. Otherwise, this is going to get too cold. And, finally, when the protostar forms, we see that it's really hot inside the protostar. So basically what happens there is that all the heat of the gas collapsing cannot escape the protostar. So everything is building up there and it gets hotter. And the molecular hydrogen inside the protostar starts increasing, okay? So one more way of analyzing this problem is by using radial profiles. So here, this is basically distance. The higher the distance is basically these areas. The smaller the distance is the closer to the center. And we're going to study the density, the temperature, and the molecular hydrogen mainly. So again, we see the same collapse, but now we see these quantities. Like outside, at the edges of the box, the temperature is very low, but as the gas collapses to the center parts, we start to see this increase in temperature. At the same time, there's an increase in density. Remember that all of this gas is falling towards the center, so there's more material. The H2 fraction, molecular hydrogen fraction, remains very low because it's being destroyed by this background radiation. At this point, atomic cooling is acting on the gas, and it produces this roughly isothermal evolution, isothermal meaning roughly the same temperature for all this evolution. And at some point, we see the formation of the protostar at the very center, and we see this increase in temperature that I told you before, that radiation cannot escape, so everything heats up at the center, reaching densities of 10 to the 18 or so. Inside the protostar, we also see an increase in the molecular hydrogen fraction. So as a summary, this whole process of collapsing gas into forming a protostar can be summarized in stages. First, the initial collapse where gas heats up, and also molecular hydrogen fraction increases. After that, atomic cooling becomes important, remaining the temperature roughly at the same value. In this particular case, the kind of atomic cooling that is acting is called Lyman alpha, which changes to higher densities to H- cooling, still atomic cooling. And after that, we see the formation of a protostar, where the gas increases its temperature, it reaches densities of 10 to 8, etc. So this is just a nice picture of the final stage of this collapse, where we see the formation of a supermassive protostar, which is what we were expecting. Now, we are interested in another thing. Remember that there were 2 points that were important in the direct collapse scenario. One is the accretion rate, the other one is fragmentation. So now at this stage, we want to study whether there's going to be more fragments, there's going to be more protostars, etc. So for that, we use this parameter that is called the Thumb-Rescue parameter. Basically, this is representing the interplay between rotation and gravity, attracting the gas, and rotation is pulling the gas outward. And what this parameter is telling us is that if the values of Q are larger than 1, it's going to be stable. If the values are smaller than 1, it's going to be unstable, meaning that it can form secondary protostars or some sort of fragments. So if we plot this quantity, Q, as a function of the distance to the center, we see that, remember, this means stable, this means unstable. So we see that there's this region here where it's like right in between. It can be stable, it can be unstable. In principle, this is telling us that this area might fragment. And what do we see? Well, here's another movie. We have all the information again, so we're plotting density. This is the moment where the central protostar forms, and we're going to see the evolution of this object. So as we evolve the object, it keeps growing in mass. We see some sort of disk around the around the protostar. We see this formation of spiral arms, kind of. Then we start to see these guys. So these are secondary protostars. So we are actually seeing here fragmentation, which is what we wanted to avoid. But that's not going to be a problem. I'll tell you later. So we see a protostellar system, many secondary protostars. We have the central protostar, and the interaction between all of them, gravity, torques, produce the disruption of the gas disk. So in the end, they all get expelled, but eventually they are going to get together again and form a supermassive protostar. So this is again the same that I just showed you in the movie, but in pictures. Just to emphasize how this evolves, like first forming a disk, then forming these arms, spiral arms, and eventually that leads to the formation of secondary protostars, until we see a protostellar system here with 5 secondary protostars and a central protostar. And that eventually leads to the disruption of the disk due to interaction between the protostars. Okay, so we do have fragmentation, but what about the growth of protostars? Here, we are plotting the mass of the protostar as a function of time. Each line is one of the protostars that we saw in the movie. But we're going to focus only in the central protostar, which is the most massive one. So this protostar starts with a mass of less than a solar mass, but eventually grows all the way to 20 solar masses. But more important than the mass of the protostar was the accretion rate. So this is what we plot now. These are the accretion rates for all the protostars, but again, we focus on the central one. And the ideal value for this supermassive black hole seeds was 1 solar mass per year, which is exactly the kind of value that we get. It varies sometimes. It can go above 1, below 1, but on average is 1. What's even more interesting is that there is another protostar here, which also has really high accretion rates. Okay, so what about that guy? Let's go back to this plot. Is this guy who's starting at like less than solar mass and it grows all the way to a few solar masses in a few years. So what about that guy? That guy is actually another protostar forming far away from the protostellar system that we saw. So that movie that I show you where you see formation of protostellar system, disruption of the disk is happening here. But the other protostar with high accretion rate is forming here. So we actually do see fragmentation at different levels. First here and also here. But that's not a problem for the accretion rate. The accretion rate still remains quite high. So one of the conclusions of our work is that, okay, we see the collapse of gas in atomic Kuhn halos all the way until the formation of a protostar with initial mass 0.1 solar masses. The protostar grows at a rate of roughly 1 solar mass per year, which is what we expected for this scenario. And furthermore, we see fragmentation, we see the formation of a protostellar system, but that doesn't seem to be a big problem for the accretion rate. So we are still good with our scenario. We still have high accretion rates and massive protostars. Okay, but now, so far I've told you that to form a supermassive black hole seed, the protostar needs to grow for about 100,000 years until it becomes a star of 100,000 solar masses or so. But the simulation that I just showed you evolved this protostar for just 20 years. Okay, so we still need to do better than this. And why is that? Because of the high densities that we reach. Remember that I told you that the higher the density, the smaller the mesh in the code, and the smaller the mesh, the more expensive it becomes. So these simulations are really, really expensive in terms of computational resources. So we need to do better. So in our second paper, we studied the growth and evolution of this protostar, but analytically, using physics and using pen and paper, basically. So we want to describe the evolution of this protostar starting from the very moment at which it was formed. So at that point, we're going to call this, we are interested in the density, the radius, and the mass of the protostar at that moment. F is because we are calling this a fragment. So the density, the radius, and the mass of the fragment. And for that, we're just going to use a simple set of equations. First, we're going to use the relation between mass, density, and volume. We're going to assume that the mass of this object is gravitationally bound, which means that all of this mass forms one single object that is being held by gravity, also known as the Jeans mass. And finally, we're going to assume that the radiation emitted by this protostar comes from the gravitational heating. Remember that I told you that as the gas collapses to the center, it heats up. So that is what's generating the radiation coming from the protostar. If we translate that into equations, they look like this. And we can solve them. We can solve them in order to obtain numbers for the density, the radius, and the mass of the fragment at the beginning of its formation, which is very similar to the values that we got from our simulation. But now, we know the conditions at the formation stage, but now we also want to study the evolution of this object. So once this object starts evolving, starts gaining more and more mass. So it grows. The density of the star, the radius of the star, and the mass of the star changes with time. But during the first time during the first period of evolution, we see that the radiation coming from the protostar comes from accretion. Remember that there is still material being accreted by the protostar, and that's generating radiation from the protostar. In the second stages of the evolution, the protostar, as it gains mass, is going to start emitting radiation, internal radiation. And that internal radiation is going to approach the Eddington luminosity. So at that point, the radiation emitted by the protostar is going to be due to internal luminosity. If we translate that into equations, we get relations between the mass and the radius of the star. And solving this equation gives us an indication of how the radius of the protostar changes with the mass of the protostar. In both cases, we see that as the mass of the protostar increases, the radius is also going to increase. And we can plot that. In both stages, they increase at a different rate, so that's why we see some sort of break here. And we can do this for different temperatures of the protostar, which is another parameter that we haven't included yet. But depending on the temperature, we see the evolution of the radius of the protostar as a function of the mass. So now that we know the initial conditions of the protostar and the evolution of the protostar, we can use that to derive the properties of sync particles. What are sync particles? So, do you remember that I told you that simulations become too expensive when they reach high densities? So somehow we want to limit that resolution. So instead of using gas particles, we're going to use something special called sync particles, which means that when the gas particles depicted here reach a limit density, we transform that gas particle into a sync particle. And that sync particle has an accretion radius associated with it. And what that accretion radius does is that all the gas particles inside the accretion radius get absorbed by the sync particle, and the sync particle grows in mass. So this is exactly what our protostar was doing in the movies. It was accreting more gas, and it was growing. So this is a really nice way of modeling the protostars if we have problems with resolution. So again, we knew the initial conditions, we knew the evolution, so we can derive an expression for the accretion radius. And this is quite complex, but what you need to get from here is that at the beginning, if the resolution is not enough, the accretion radius is going to be constant, but eventually it's going to depend on the mass, meaning that as the protostar grows in mass, the accretion radius is also going to be increasing. Okay, so during the second part, we describe the initial state of the protostar when it's formed. We also derive a relation between the protostellar radius and mass, meaning that as the protostar increases in mass, it also increases in radius. And we use that to find a subgrid recipe for the accretion radius of a sync particle that we will use later. Because these sync particles can be used in simulations to limit the resolution and being able to follow the evolution of the protostar for a longer time. Okay, so now with that model in mind, we can follow the evolution of this protostar for a longer time until it becomes a supermassive star, and that's what we did in part 3 of this dissertation. So again, coming back to the problem of resolution, we have really huge densities, and somehow we want to avoid this because this is computationally expensive. So what we do instead is we limit the resolution, and as I told you before, we're going to use something called sync particles. So once a gas particle reaches a threshold density, which is the limit that we are imposing, it's going to become a sync particle, and that sync particle will have an accretion radius associated. And this sync particle is going to grow in mass, and this is a really nice model for the central protostar. And we don't use just one threshold density, one limit, but we use 3 different ones. In that way, we're planning to follow the evolution of this object in the early, intermediate, and late stages. So the lower the threshold density, the longer in time that we can evolve the simulation. Again, coming back to our simulations, we need to model dark matter, gas, chemistry, and now in addition, we added these sync particles that depend on the threshold density and the accretion radius. So I'm going to show you here movies of the early, intermediate, and late stages of this supermassive object. These are really small scales, these are intermediate scales, and these are large scales, because the late stages means that the object is more massive, so it's going to be bigger too. And in the early stages, the object has less mass, so it's going to be smaller. So this is what happens in the early, the intermediate, and the late stages. So again, we see this collapse of gas towards the center. In this case, I'm setting the colors in such a way that all the bright yellow dots are the gas particles above the threshold density, which means that all of these gas particles get accreted by the zinc particle. So all of these yellow dots are going to be part of the zinc particle, and the zinc particle is going to grow. Okay, so now we have the three models. We can explore how their mass increase as a function of time. So we have three lines here: early stages, intermediate stages, and late stages. And at each stage, we explore just a range of masses. So for example, in the early stages, we go from like 10 solar masses until a bit below 1,000 solar masses. The intermediate stages go from a few tens of solar masses until roughly 10,000 solar masses, and the late stages go from a few hundred to roughly almost 100,000 solar masses. So in general, if we just take the whole picture of early, intermediate, and late stages, we see the evolution of this object all the way from 10 solar masses or so until it becomes a supermassive star of 100,000 solar masses. Again, what's more important here is the accretion rate, so that's also something that we want to explore. Remember that the value that we're looking for is roughly 1 solar mass per year, and in this case we are getting values of 2 or more, sometimes a bit below, but on average 2 solar masses per year for every single simulation, which is ideal. This is exactly what we were expecting. So this is really nice. We have the formation of a supermassive star of roughly 100,000 solar masses with an accretion rate of 2 solar masses per year. So we've used simulations to study the early, intermediate, and late stages of this object, and we follow the evolution of this object from masses of 10 solar masses all the way until 100,000 solar masses or so, at a rate of 2 solar masses per year, which is really nice. So everything is working out for this scenario of the direct collapse. But one more thing that we want to study is how the radiation coming from the protostar might affect this evolution. So for that, we're going to have this picture in mind, that as the protostar grows, it starts emitting radiation. And that radiation ionizes hydrogen around the protostar. So neutral hydrogen plus some energy becomes a proton plus an electron. So it's ionizing radiation. This ionizing radiation is going to depend on the mass of the protostar. So the bigger the protostar gets, the more ionizing radiation it forms. Eventually, this is going to lead to the formation of what we call an H2 region, a region where inside this, the gas is ionized. And we want to characterize this H2 region by what we call the I-front radius. So the I-front radius is the surface at which ionization is in balance with recombination. What does that mean? That inside this area, ionization is winning. That means that most of the gas is ionized. But outside, recombination are winning. So that means that most of the gas is neutral. And we want to see how this evolves with time, how this H2 region grows and how that might affect the accretion rate of the protostar. So in terms of equation, we have recombinations, we have ionization, and here is the radius of the ionization front, which is basically the size of the H2 region. So we can plot the size of this H2 region as a function of time and also as a function of mass of the protostar. So the more massive the protostar, this one, the bigger is going to be the H2 region, which is expected. All of this picture that I'm telling you is only valid until these dotted lines. These dotted lines are the shock radius. So the shock radius is another region of the halo where inside this shock radius, the gas is being heated up and it's trying to expand. But from outside the shock radius, all of the gas is collapsing. So we have this fight between gas trying to expand and gas trying to collapse, and that forms a shock, and that's the shock radius. So why it's important? Well, because the I-front radius, the H2 region, is going to grow eventually. It's going to keep growing as it gains more mass, and eventually it's going to hit this shock radius at what we call the breakout time. Why is it called breakout time? Because then radiation breaks out. So finally, once the H2 region crosses that shock radius, the radiation coming from the protostar just escapes from the halo. And we want to analyze how that behaves in our simulations. So we are using here data from our simulations. We're using the mass of the protostar. We're using the time at which the protostar achieved that mass, and we are plotting it here in these lines: early, intermediate, and late stages. For comparison, the shock radius is plotted here in dashed lines. So this is telling us that as the H2 region expands, it hasn't reached the shock radius yet, which means that it hasn't escaped from the halo. It's still inside the halo. For comparison, we have plotted also here 100 times the radius of the protostar, just to quantify how far from the protostar is the ionization front radius, or the H2 region. So here, the H2 region crosses 100 times the radius of the protostar well before the mass reaches 1,000 solar masses or so. So we can say that it's the ionization front radius is way far from the protostar at that point, so it has detached from the star. Just to give you a mental picture of what's going on here, at the beginning of our simulation, we have the H2 region is ultra compact, it's really, really small. We have this dotted line, which is 100 times the radius of the protostar, and we have this dashed line, which is the shock radius. But at the end of the simulation, the H2 region grows beyond this 100 times the radius of the protostar, but it hasn't reached the shock radius yet. So it has detached from the protostar, but it's still trapped inside the halo. One important point here is that all of this model that we've done so far is with data from our simulation. But in principle, if we really want to simulate how radiation might affect the growth of the protostar, we need to include these equations into our simulation to make everything self-consistent. And this is work that we are doing so far. So this is just showing densities. At the very center, there is a zinc particle. The zinc particle is injecting radiation into the surrounding gas. And these are pictures of a number of photons. Well, it's density. It's the same as number of photons. So as the protostar grows in mass, injects more and more photons, and the region of photons injected becomes bigger and bigger. So in the future, we want to fully couple all of these equations to actually get a description of the growth of a protostar with radiation included in our simulations. So from this part, we've learned that radiation detaches from the protostar at the end of the simulation, but radiation hasn't escaped the halo yet, so it's still trapped inside the halo. But with the caveat that we actually need more simulations to actually simulate the evolution of this object under radiation. So in this dissertation, we've been exploring this direct collapse scenario in different stages. In the first work, we analyzed the collapse of an atomic cooling halo, collapse of gas into the center, all the way until the formation of a supermassive protostar. That supermassive protostar is unstable, which leads to the formation of a disk, spiral arms, and finally a protostellar system. But remember that even though we have fragmentation, accretion rates are still quite high, so it's still good. In the second paper, we analyzed the intermediate stages, how the protostar evolves, the radius of the protostar as a function of the mass of the protostar. And we used these models to get a prescription for the accretion radius of zinc particles that we will use in our simulations. So in the next set of simulations, we use this accretion radius recipe to study the early, the intermediate, and the late stages in the formation of a supermassive star, all the way until it becomes an object of more than 10,000 solar masses. In the current work that we're doing, we're trying to explore how radiation might change all of this picture that we have in mind, coming from the protostar, how it can push the gas outwards and change the accretion radius. But for that, we still need more simulations, and we are working on that so far. Finally, the final path to become a supermassive black hole seed is some sort of instability, and simulations haven't reached that point yet. So in the future, ideally, we would also like to simulate this stage, although it's quite hard. But so far, the direct collapse scenario looks very promising, and we are getting supermassive stars of 10,000s of solar masses. Thank you.
Questions for Fernando?
A couple of questions related to the first point, the cooling part. So one is you assume that there is a source of Lyman-Werner photons,
Yes.
and so what kind of radiation field, how intense does it have to be to suppress the production? And the second question is, to what level would you have to pollute the gas with metals before this picture breaks down?
Yeah, so in the first case, like the question was how intense this background radiation needs to be in order to destroy a molecular hydrogen. It actually needs to be quite high because, well, studies don't agree on a single value, but values might range from 5 to a few hundred, few thousand in units of the background radiation. So we are assuming that that background exists. It might be from a neighbor galaxy or from stars formed inside the halo at an earlier time. In general, we are assuming that background, and we are including a quite strong background in order to just suppress the molecular hydrogen. Just kind of a numerical experiment to see if this scenario works. And in the second question was about the metals. So yes, that might also happen, and we are assuming here that this halo is metal-free because metal cooling also will drop the temperature. So yes, this is another assumption that we have. Besides the background radiation, we're assuming that there are no metals.
But at what level would you have to, with one supernova...
Basically like no metals. Basically no metals and a very strong background radiation. It might happen, it might not happen, but it's one theory for the formation of black hole seeds.
We're all hoping that the James Webb Space Telescope will be launched in a year and a half or so. Do you think about whether these supermassive stars can be seen directly with JWs?
Yes, so that's part also of the project, trying to make observational predictions for this supermassive star, because it would be really nice to use James Webb Telescope to observe like signatures, radiation coming from the protostar, and see if it exists. Because so far all the work that we've done here is just theoretic, just simulations, but we need the confirmation from the observational side. So yeah, that's among our plans to try to make predictions for the future observation.
Do you expect to derive new constraints on the formation of massive stars as opposed to supermassive stars along the way? And the question of, our top 3 stars primarily 100 solar masses or thereabouts?
Yeah, so I would say that this very particular scenario, as we already said, it requires a lot of requirements beforehand. So this is a very particular case of supermassive star. There has been some other works on POP3, how massive they are, and they also have their assumptions. But in general, I don't think we can quite relate this work to a kind of prediction.
Yeah. So is it mostly coincidence that the ionization front radius just almost reached the breakout radius at the end of your simulation, or was there some self-regulation mechanism there?
I think our simulations still don't include radiation, so this is just an approximation. And we will expect that at some point the ionization front radius crosses the shock radius and escapes from the halo. And that's what we were expecting before doing the analysis. at, I don't know, like 1,000 solar masses or so, but it hasn't happened yet according to our data. But we require more simulations in order to like have a conclusion to that. But in general, we would expect this to escape before the massive protostar reaches 100,000 solar masses.
Can I ask, like, from your simulations, when you form these supermassive stars, what are kind of the fraction that is it possible that some of them form in binaries?
Yes. So well. Really good question here. So yeah, so in principle, this kind of fragmentation at larger scales might lead to some sort of binary. And luckily, we didn't have the computational power to follow this, the evolution of this simulation. But in principle, all of these protostellar, the protostellar system is gravitationally bound. So this should be forming one object, and this should be a totally different object. We are not sure at what time they are going to merge, or if they are going to merge at all. But yeah, forming a wide binary system is a possibility in this kind of simulation.
More questions?
Sorry. So when do we expect these supermassive stars to start fusing, or like is that?
Yeah, so quite earlier in the evolution actually, like between 100 solar masses or 1,000 solar masses or so, they should be start forming like nuclear fusion inside and become like a proper star more than just a protostar. So that's also going to be part of the current work, like trying to model that emission coming from the protostar. But yeah, you're totally right.
To change the outcome?
Yeah, in principle, yes, it should change. I don't know how much though. We don't have an intuition for that, but it might change in terms of fragmentation, in terms of accretion rate, but yeah.
Did it follow the evolution of the secondary protostar, the second state, and then the fragment, and what would happen to that?
In this one?
Yeah, the fragmentation, the secondary.
So in this case, all the analysis that we performed is saying that they are gonna get together again, come back to the center of the halo, form a massive protostar. About this one, we don't know yet because this is in the early stages of formation. So we are assuming that here, to this protostar, is gonna happen something similar to what happened to this. So in principle, we would expect to see some sort of protostellar system here too. But again, we didn't have the power. At this point, the simulation just became too expensive, so we just couldn't keep evolving the system.
Any more questions?